Hi, I'm Lars Jorgensen with ThorCon.
What you see here, two 500 megawatt power plants put into the shape of a large ship.
That can compete directly with coal, can be deployed quickly.
And it includes everything for the power plant, all the way through the electrical switchyard and hooks directly to the transmission lines. All these little circles are coal plants, either operating or under construction or permitted and getting ready to build. Developing nation, as soon as it can afford power, is going to buy the least expensive power, which in today's world is coal. So there's a lot of plans to expand with coal. Our goal is to give the nations another choice, nuclear power at a price directly competitive with coal. In Indonesia, nuclear power is reasonably well accepted, up to 77% pro-nuclear attitudes.
What we've been doing with Indonesia, they've got light water reactors, but they don't have any regulations for advanced reactors. So they've been rewriting the regulations to allow non-light water reactors and MSR within their guidance.
Indonesia is the world's fourth largest country by population, and it needs a lot of new electricity.
Before that trip, they had a blackout for 8 hours in the capital city. We became popular in the press because the 8-hour blackout was kind of a shock to the capital city.
This shows you a coal plant with a day's worth of fuel for the coal. It needs 10,000 tons of fuel a day. And it generates about 1,000 tons of waste a day. Compare that to a nuclear power plant, and we need about 0.1 tons of fuel a day and generate the same amount of waste. We need a lot less fuel, a lot less mining, and you generate a lot less waste. These two drawings are to scale. Once you get past and have generated the steam, converting the steam to electricity is the same. We're basically the same steam conditions as a coal plant. That was done deliberately. There are a lot of companies that supply turbine generators for coal plants, so the price competition there is pretty aggressive. That helps us hold the cost down. But the other half of the plant is taking the fuel and turning it into steam. Because you've got so much material to handle, the coal plant is quite large, much larger than our nuclear island. And that leads to lower capex and lower fuel costs. So we believe that we should be able to compete directly with coal. How do we do this? A process developed in the US at Oak Ridge National Labs, done by the same man key in developing the light water reactor. But he felt that we could do a better job. What he built was a reactor based on molten salt rather than water. A light water reactor uses water as its primary coolant. It wants to turn to steam. Now, if you get over 100 degrees C at 1 atmosphere, your water will turn to steam. But 100 degrees C is not hot enough to generate power, really. So they get it up to 300 degrees C, but to keep it liquid, they have to put it under 160 bar pressure, 160 atmospheres of pressure to squeeze it in, which means you need thick pipes. If anything goes wrong, that steam wants out. It's going to expand and deliver a pressure wave to whatever vessels are containing it. It makes the engineering more difficult.
The molten salt reactor experiment was one of the most important, and I must say, brilliant achievements of the Oak Ridge National Laboratory.
We're using salt as our primary coolant, 500 degrees C or so. It will melt and become a liquid very much like water, but it won't boil until 1400 degrees C. We operate between 565 and 704, so we have about 700 degrees of margin before we boil. In other words, we will always be a liquid. We will never turn to a vapor. If there's any kind of problem, there's no big pressure. And if there is any kind of leak, it's going to just spill on the floor like if you had a water leak. Oak Ridge actually built an 8 megawatt thermal reactor core to do the prototyping experiments. When they had finished that and learned everything they could, they developed plans for what to do next. They had several different proposals. The most conservative one was the molten salt demonstration reactor, the scale up of the molten salt experiment reactor that they already did. That one was to be 350 megawatts electric, not to be a breeder, be a single fluid reactor. We have more materials to choose from, and we're going to shift to be more of a shipyard production. Computers are a lot more powerful now. We have a lot more software, so we can use that to improve the design. We've taken that same idea, and that's what we're marching forward with, is to do it as simple as possible, to get to the market as quickly as we can. And our main focus is, of course, safety, but keep the cost down. Where's ThorCon come from? It's a THORium CONverter. You can have plants generate their own fuel. So they will take a common material like thorium or uranium-238 and convert it to fissile. That kind of a reactor is known as a breeder, something that the world has been trying to do for quite some time. The US tried and gave up. France tried and gave up. Japan tried and gave up. The Russians have managed to get a couple going, but it's hard. It's quite difficult to get a breeder to really work. We're satisfied with a converter. So it means that we have to keep adding fuel. We have to buy enriched uranium and keep adding it. Our primary concern is cost. In 50, 100 years, that is a problem that does need to be solved, but it's not a problem that needs to be solved today. Uranium-235 will finish it by itself, so that's what we have to buy. But we can also have thorium-232, and when it gets a neutron, it'll become 233, which through a couple of decay steps will become uranium-233, and that's also fissile. And there's a similar process with uranium-238. If you add a neutron, it becomes 239, and then a couple of decays, it becomes plutonium-239, which is fissile. 3 ways that we get fissiles in our process. The core is about 85% thorium and 15% uranium. 25% of our fission comes from uranium-233 that we got from the thorium, and about 25% comes from different flavors of plutonium that we've generated. So we generate about half of our own fuel, and we have to buy about half. Over time, I can see R&D projects to increase that, but the key emphasis now is get the plant built as soon as we can. This is a picture of the full power plant, built in the shape of a hull, based on tanker design. Over here, we have the fission island, this little strip here. On this side of it, decay heat removal process and heat exchangers before we get to the main turbine and then the generator. In front of the turbine, you see low pressure feed water heaters, the deaerator, and then the high pressure feed water heaters. You've got to heat up the water before you put it into the steam generator. And that's the steam generator there. Once you get through this whole section, you've got electricity at 25 kilovolts, but also about 25 kiloamps. In order to put that on a transmission line, you need to step it up, typically to 275 kilovolts or perhaps even 500 kilovolts, and the current will step down proportionately. So that's what these transformers are. We have 3 transformers for a 3-phase grid, and we store a 4th transformer as a spare because the transformers are probably the most likely component to break, and we don't want the delay. If a transformer goes out and needs to be replaced, we want to be able to do that very quickly right on site. You have the switchyard gear with the circuit breakers and such. You're parked right near the shore, and you're going to have an overhead transmission line. We also have an option, a subsea cable. So if you want to park 5 or 10 or 20 kilometers offshore, that's perfectly feasible. If you're going to park a long ways offshore, for example, we looked at one site in Europe between London and Belgium, and there we would have to go 50 to 80 kilometers. And for that, we probably want to go to high voltage DC, which is something you can also put in as an option into the switchgear yard. You can see the big seawater pumps, about 15 meters tall, so they're not small things. A big pond of water, we use that to remove the decay heat. Another pond of water here, which is a backup for that. But as you look at this, you can see that the fission island is a rather small part of the whole job. It includes even a desalination plant, makeup water for the turbines. We have our own built-in crane to move stuff around. Everything is accessible by hatches. See the yellow squares? Those are hatch covers. Because we're at low pressure, we can have very large doors. Those doors are 10 meters by 10 meters and about 500 tons. But the crane can lift them, and then it gets direct access to the components inside the power plant so that we can change out anything that needs to be changed. For example, the steam generator typically will last about 30 years, and so we anticipate that we will have to change it out from time to time. We have seen in the US, light water reactors have reinforced concrete containment domes. Because the pressure can get so high, the door in it's small, not big enough to take the steam generator out. So when they've had to replace the steam generator, they've had to cut through the concrete to get to the steam generator. They even had one power plant that got lost because when they cut through the concrete, they didn't detension the steel cables first. And so the concrete and steel delaminated and they couldn't repair it. So they lost a power plant that way. For us, it's just a door. We lift it. So we have 2 cans, one that operates and generates power. The other one that has finished his job of generating power and is now in cool down mode. Inside the can is the moderator, that's graphite, and that will wear out after about 4 years. then take the fuel, move it over to the other cans, let the radiation decay away before we take it out and ship it back for replacing the graphite. You can also see heat exchangers here and the steam generator. This is the silo hall region here, right above the reactors. Dose rate is low enough that workers can be there full time. In fact, you probably will get less radiation being inside here than if you were up on top. The stuff above will block the cosmic rays. And you can see the motors are accessible up here. There's some variable frequency controllers that also control the speed of the motors. All that sort of thing we want to have access to, so we put them up above. Fuel, spent fuel, is below here, which lets us be both a radiation barrier, but also a safeguards barrier. The door that lets you get to these components down here is 400 tons and would have IAEA safeguard alarms attached to it. You have no reason to want to open those doors on short notice. So every 4 years, you need to call the IAEA and tell them it's time to refuel, let their inspector have a chance to come, and then open it up, do the refueling, and then close it, and the inspector then reseals it. There's also seals and alarms from underneath, so there's no way to disable them. This is an overhead picture where you can see the different pieces from the nuclear island, the heat exchangers, the steam generator, the turbine. You can see the turbine is a pretty big component, and then the generator, and then the switch yard. Over here, you can see the decay heat removal ponds. These are dedicated just for the decay heat. They're not used for the primary heat path. That primary heat path uses one through ocean water cooling. This gives you the temperatures and the pressures in the various loops. We have 4 loops. The primary loop has the fuel salt in it, along with obviously the fuel, but also the fission products will be there. They stay inside the can. The secondary salt here goes into the can, into the primary heat exchanger, then comes out noticeably hotter. It goes in at 454 and comes out at 621, and then goes around to a secondary heat exchanger. The secondary salt is a salt that is compatible with the fuel salt and is always at higher pressure. So if there ever is a leak in the primary heat exchanger, it'll leak secondary salt into the primary loop rather than the other way around. That way we keep the radioactivity inside the can. Then the third loop is nitrates loop. It uses something we call solar salt. It's used in thermal solar plants. It is very compatible with moisture. If there's a leak in the steam generator, it won't have any noticeable chemical reaction with the solar salt. And also if you have tritium, which we will get some tritium because we have fission and we have beryllium present, the tritium can go through hot metal. So it'll go through these heat exchangers, but when it gets to the oxygen that's in the nitrate, it'll get trapped and it'll stay there. Then that goes through a rather standard turbine generator. Because we don't have so much material to move, we don't have machinery moving 10,000 tons and scrubbers and all that, our house load is smaller than a coal plant, and we don't lose power out the flue because in a coal plant you have exhaust gases, which you lose about 10% of your energy. We don't have that. So we get efficiencies that are higher than what you'll get in a typical coal plant. Typical coal plant will get about 44% efficiency. If we're in seawater that's at 30 degrees C, it's pretty warm seawater, we get 46%, 46.5%. And if we're at 20 degrees C, it'll be about 47.7. Here you get to see a little bit better scale of things. You can see a couple of people here. Here we've taken off the can so you can start to see a little bit of what's inside of it. That is the reactor vessel itself there. Here's the can. This is really where the heart of the action goes on. You have the reactor vessel, we call it the pot. It's full of graphite. It's about 90% graphite. Graphite serves as a moderator. It slows down the neutrons, gets us to be critical. So you have a spot here which is nearly spherical in shape, gives us our critical mass. As soon as you leave there, you're in a smaller pipe. You're not critical anymore. So the fission will stop very quickly as the salt leaves. Goes up into this header tank where you have a big pump, and that pushes the salt around into this blue one, which is the primary heat exchanger. So it goes in at 704, the salt comes out at 565, and the secondary salt goes in and out of that same heat exchanger. We're moving the heat from fuel salt to the secondary salt. A lot of the fission products will become either xenon or krypton. One of the nice things about liquid-fueled reactor is xenon and krypton do not have much solubility in the salt at all. They will bubble out. They're going to come out. So we go ahead and help them come out and then have a sweet gas of helium to push it along into these off-gas tanks where radioactive xenon and krypton can decay away. And after it's decayed for about a week, it'll come out of there and go into additional tanks. At the very bottom here, you can see a little gray thing. That's the freeze valve. The salt is flowing around in this loop here, but there's a pipe that leads from the very low spot in the primary loop. And that pipe has a section that's been flattened and has cold helium sprayed on the outside of the pipe. It keeps that spot of the pipe cold. That freezes the salt and makes a plug that keeps that pipe plugged. If at any time you cut off the flow of cold helium, that plug will melt and the fuel salt will drain by gravity down into the drain tanks here. 32 of them that are spread around in a circle. The exact opposite of forming critical mass. We spread the fuel out as much as we can. It also has a lot of surface area to volume ratio, so that there's a lot of surface area to radiate heat from the drain tank into this blue area here, which is our cold wall. So the cold wall is steel, and then about a half meter of water and steel. So the heat that's in the fuel will heat up the outsides of these drain tanks, and then it'll radiate across this argon gas filled gap, heat the steel that's on the cold wall, which will boil the water that's on the other side of that steel. Those bubbles will go up. So the heat will flow naturally from these out and up. You can see more detail of the freeze valve designed and debugged by Oak Ridge for their MSRE. We took advantage of all the work they did. We needed 4 times the throughput, so we just put down 4 copies. There you can see the flattened freeze valve. Bubbles form in this cold wall. They will go up, and then they go over to this radiator, which is sitting in that pond of cold water. That will heat up that water and cause evaporation. Will condense the steam that's gone up the cold wall, and that will then be returned to the basement, where it will come back in at the bottom. There are no valves in this system. It's always on. There's nothing an operator or prime minister can do to stop it. Freeze valve will open, the salt will come down into the drain tanks that are hidden by this nice pretty blue thing, and then the heat will be pulled out from there. And all of that is something that requires no electricity, requires no machinery, there's no operator action, no maintenance worker can leave a valve in the wrong spot. Because what we've observed is that every one of our nuclear accidents have involved people doing the wrong thing. So we've made it so that if a person does the wrong thing, the reactor will, by physics, shut itself off and remove the decay heat. In addition to this passive cooling system, we also have a lot of spare basement water. If a terrorist came along with his scuba gear and he welded shut that pipe, there's a blowout panel. The water that goes in here and turns to steam would expand and put pressure on and blow out that panel. And then that will go into a quench pipe that's in the basement water here. So then we would be boiling off the water that's in this section and dumping it into this basement. And that will give us 4 months to respond. In that case, though, you are boiling away the water that's part of this cooling system. So you got to get there. But that would be if a terrorist attacked the power plant, and I would expect you'll be there within 4 hours, not 4 months. This is on the order of 7 meters across and about 12 meters tall. And that's providing enough power for 250,000 people. So you get a lot of power out of a relatively small space. We have 3 shutdown rods. Any one of them can shut down the power plant and stop fission. You can see them here. They're not very large. They're just about this big. Triple redundancy there. Operate with a magnetic catch. If you go over temperature, the electricity to the magnetic catch is cut off. The rods will fall by gravity. I mentioned that xenon and krypton want to come out. They are about 40% of the fission products. We can grab 25 to 30% of all the fission products by pulling off gas off. There's a gas headspace above the header tank, around the tank pump, to let the xenon and krypton come out. And then we have a sweet gas at about 2 liters per minute. The xenon and krypton are generated at about 1 liter per hour. Those go into these tanks that are still inside the can to let the most intense part of the radioactivity die down for about a week. It goes over into these 2 very large tanks, so that's almost 500 cubic meters worth, where the longer-lived fission products will decay away. By the time we get to here, we'll be down to just the tritium and the krypton 85. That will go over to a cold trap, which will separate out the xenon, which at this point is no longer radioactive. Put that into bottles. and it will also separate out the krypton and put that into a bottle. And then there's a getter to gather any oxygen or tritium that have leaked into the system. Salt is not corrosive unless you get oxygen and moisture in there. So we continuously remove down to parts per million all the oxygen and moisture. Tritium is generated, and some of it will go with the salt, so with the off gas, we'll grab that. And then we'll compress it and send it back around. So we have a closed loop for our helium. Inside the can is graphite, it's the moderator. The neutrons that strike the carbon atoms will move them out of place, and eventually that makes the graphite swell. So it'll first shrink by 2%, and then it'll start swelling. When it gets back to its original size, we say, okay, it's done now, and we need to replace it. We don't try to replace it at the power plant site. Instead, we leave the graphite inside the pot, which is inside the can. We take the whole can out, and we put it into a specially designed ship, which we call the can ship. It's designed for international standards for transport of nuclear materials. This ship will also bring a replacement can. So every 4 years, the ship comes by, brings in fresh cans, takes out the old cans, it brings in fresh fuel, takes out the old fuel. And that's what this big sturdy crane is for. That allows us to do a thorough inspection of all the parts inside the can so that we can replace any other parts that are wearing out. The bearings will have a life of about 16 years, so they'll have to be replaced periodically. There's a filter in there that probably gets replaced every 4 years. It's just a few things that will need to be replaced regularly. The primary metals generally will not need to be replaced. This ship can take shallow draft, so it can go up rivers as well as go through the ocean. For Indonesia, I think we'll be almost entirely ocean-based, but in many other places, we need to be able to go up major rivers. Safety is intrinsic. That is, it's going to do it automatically without any electricity, people, or machinery. First one is to stop the fission. We talked about shutdown rods dropping automatically, that backed up by salt heating up, losing its reactivity as it gets warmer. So that stops the fission. That's job one. Job two is to remove the decay heat by having the fuel salt drain into the drain tanks and then radiate their heat into this wall and then into the decay heat removal pond. And the third job is to be sure that we keep all the fission products contained. The fission products are mostly inside the primary loop, but definitely inside the can, which is inside the silo, inside the hull. Can is 25 millimeters of steel, but it has no pressure. It's the same pressure on the outside as inside. And it doesn't have corrosive gases. It's got helium or argon around it. So it's in a very benign environment. The drain tanks are thinner. They're about 10 millimeters thick. But again, the same thing. And they're small diameters, so their hoop stress is small. The can is at about 350 C, so it's not even very warm. The drain tank does get warm when the salt is put into it, but that doesn't last for a long time. So the cumulative creep damage is small. Beyond the first barrier, we have a second barrier, which is the steel that's part of the silo wall and the floor that's above it. That's also a gas-type barrier. It's at 140 degrees C and a few bars pressure, so it's under no stress as far as steel is concerned. Unlike a light water reactor, if there is an accident and somehow the salt gets through the first barrier, it doesn't push a whole bunch of pressure onto the second barrier. And the final one is the ship hull itself. 25 millimeters of steel, and then 3 meters of concrete, 25 millimeters of steel. So it's a very robust barrier, and it also serves as the barrier against aircraft strain. What would happen to this plant if you had something like Fukushima? When an earthquake happens, it sends out 2 waves. The first travels very fast, but doesn't induce much motion. In fact, most people wouldn't notice it. But we have sensors to notice it, and they have them at Fukushima. So when that first wave hit, the sensors saw it and dropped the shutdown rods and turned off fission. When the main earthquake hit, the fission had already been stopped. The plant was in shutdown mode. The plant survived the earthquake just fine. So for the next 45 minutes, cooling down and removing the decay heat. But then the tsunami hit. And when the tsunami hit, that took out the cooling system. Then because it wasn't being cooled, you had problems with decay heat causing the zirconium to release hydrogen and then the hydrogen explosion. For us, if we had that same sort of scenario, the earthquakes would drop the shutdown rods and start a drain. All fission would stop. We would lose the primary cooling, but now we're draining. The maximum salt temperature gets to 750 C, which is still below even where you start accumulating any creep damage. You're still within spec for what stainless steel can tolerate. We could have a worse accident. Imagine an earthquake so bad it knocked out all of the electricity right away. That's noticeably worse. It's really a big benefit to have that first 45 minutes of cooling. That kind of an accident would take out any light water reactor around. But in our case, we lose the power, therefore the shutdown rods drop, the freeze valve starts to melt, takes about 10 minutes for the freeze valve to melt, and then fuel salt drains and it passively cools, because once it's in the drain tanks, the cooling is automatic. In that case, we hit a maximum temperature of 850 C, create a very, very slight amount of creep damage. The worst one would be instant station blackout and triple failure on the shutdown rods. So all shutdown rods fail and you have lost all electricity instantly. In that case, the temperature starts climbing, and what stops the fission will be when the salt gets to 800 degrees C. That's about 80 seconds, and then it climbs from there. So at the end of that very bad accident, the salt would have gotten to 1,000 degrees C, and we would have suffered creep damage for about half of 1% of the steel life. Obviously, since the shutdown rods didn't work, we would say this can is condemned and replace it. But there was no release, even in this very worst of accidents. I told you we designed this like a ship. North Atlantic storms can give you 9-meter tall waves, accelerate your ship by 1 G. Here you see a finite element model of the ship. The blue line that's sort of waving along is the wave. And we did a bunch of different wave patterns. We had to do a little bit of adjustment to add some high strength steel here and there where there was the biggest stress. But we were able to design this to tolerate 1 G forces. Designing it to be able to be towed meant that we've designed it to tolerate quite severe earthquake. What happens with an aircraft strike? For the vast majority of the plane, it just crumbles. Planes are made deliberately to be as light as possible. So when they hit something solid like what we have, the plane itself will just crumble to dust. But the engine has some sturdy components in it. What we actually modeled was the engine itself, flying at 200 meters per second, which is a pretty good clip to try to fly when you're down at sea level. That's getting you pretty close to supersonic speeds where the plane will just rip itself apart. The engine did penetrate the steel on the outside. Then it bumped into all that concrete. It pushed the concrete enough that it dented the inner wall by 300 millimeters, but it didn't penetrate the inner wall. So we were able to survive maximum speed right at 90-degree aircraft strike. The next question is, how are we going to deal with earthquakes? We're going to be resting on the seabed, not floating. So we will feel a little bit of the earthquake, but a fair amount of sand below us. If it's not natural sand, then we'll prepare the seabed to put that in. The sand won't transmit strong forces. If you try to move something hard against the sand, you're going to slide over the top of it rather than moving the whole sand. So you can have a strong earthquake here at over 1 G. The sand will give way so that the hull only sees about 0.3 Gs. In addition, the can is suspended with basically shock absorbers. So there's an attenuation between how the hull moves and how the can moves. Another concern we would have to watch out for is tsunamis. We are, after all, at sea level. The hull is 30 meters tall and typically will be in 5 to 10 meters of water. So you'll have 20 or so meters of freeboard. Tsunami comes along and it's less than 20 meters, it's not going to do much. We would recommend you not put yourself in a specific tsunami zone. To get a large high wave tsunami, you really need a land structure that looks like a lens to focus that tsunami and focus all that energy to a small space. There's relatively few places like that, so most of the places you could choose would have much, much smaller tsunamis. If you are in a place that has a larger potential, you can put in heavier ballast, which means it's floating to the site, and then we ballast it down. We add water and cement to make it heavier so it sinks to the bottom. What about the waste? For nuclear power, waste is actually one of our advantages compared to our competitors. It's only when you compare it against perfection that you can try to make that a big problem. This is a picture of the waste from a coal plant. A coal plant generates about 100,000 times more waste than a nuclear plant. They generate so much waste, they can't afford to put it in containers. They make big piles out of it, make lakes out of it. And even in the US, when there's a storm, turn into slush and break its dam and go wipe out a town. It's happened more than once.
crews are using heavy equipment to clear away sludge that inundated a neighborhood near Harriman, Tennessee. 5.4 million cubic yards. Coal ash residue that comes from burning coal to create electricity at the power plant that is run by the Tennessee Valley Authority. That ash is now entered into the neighborhood, entered into the land, and most importantly, into two rivers here in the Tennessee River watershed.
We've never had a problem with nuclear waste. This is all the waste from a light water reactor, 28 years at 450 megawatts. And you can see people standing here. It's not a radiation area, just air-cooled. They're basically just sitting there in a parking lot. The plan is that this is Baton's responsibility, and they will find an uninhabited island, and that will provide enough storage to let you store all of the waste from all the nuclear power plants if you used only nuclear power for generating your electricity for the next 100 years. That is the baseline plan. So the fuel lasts in the plant for 16 years. It cools on board for at least 4, maybe up to 12 years more before we try to ship it. We put it into a special shipping cask, and we put that on the can ship, and we take it to wherever that storage site is. There's an option where we can add 5 meters of length to the hull, and then we can store it on board. What we've seen in practice in the United States is the government never got around to building the interim storage area, so it's been stored on site. So if you want to do that, we can do that as well. We can store inside the hull, just in 5 meters of space, 80 years worth of operating the plant. That also helps you visualize that this is not a lot of stuff. Why do we build it like ships? Because that's what we've done before. This is the world's largest double-hull oil tanker. Our founder designed it, supervised its building, and operated it. He built 4 of those, and the last one took less than a year to build. It's about twice the size of one of our power plants. We have experience. We know how to build this. We know how to design to make it suitable for the yard to build. And that one cost $90 million to build. We've got an estimate from a shipyard for building 75% of the cost for $350 million, which is in line with our estimates of about $1 a watt. What's a shipyard look like? Well, they have panel lines, divide the design down into blocks that are 300 to 500 tons each, and they'll be worked on in parallel. So you could have 100 different pieces of the power plant being worked on in parallel. When the blocks are all finished, they are assembled in dry dock into the whole ship. You can test each block as it's built. So each block, when it's finished, we're going to test to be sure that all the connections are there and inspected and such. If any block didn't pass, we can go back and rework that block while the other 99 blocks keep on continuing. That's how the shipyards can sign contracts for firm fixed price, for fixed schedule, and plan on building this in a year. That's in sharp contrast to building light water reactors where a build time of 10 years is pretty common. What you see here in this picture is about 5 welding machines and 1 person. In the yard, they actually run about 80 machines in parallel and 1 person operating it. On this side, you see the shipyard itself. One of these shipyards could turn out 21 gigawatt power plants each year. There's enough surplus capacity in the world to deliver about 200 gigawatts worth of power plants with our design a year. There's a lot of surplus shipbuilding capacity in the world. What that says is we can build these power plants to satisfy the full demand. Whatever people need, we can build them that fast. That's in contrast to a light water reactor where you've got these thick forgings that only a very few people in the world can make. I think there's 1 in Japan, 1 in France, 1 in China. They're limited in how fast they can build out. But we can build out. So where are we with our program? Currently in design. We expect it'll take about 1 year from when we get full funding to be able to finish the design, finish specs, get them reviewed by vendors, get the bids in, and be ready to build something. And then about 1 year to build what we call a pre-fission test platform. We test that one for a year. Again, it's pre-fission, so there's no fission going on, so it's not intensely radioactive. Once we've debugged, we can go to demonstration plant. So this would be a 500 megawatt power plant. That would take about a year. And then about 2 years for testing that plant. At that point, we'll be 6 years into the program. We expect to do this in conjunction with the regulators, so they will review the test plans, they will be present to witness the tests. So when we finish the tests, they will already have finished their regulatory work. And then we need to write up the last little bit of the last test. So we should be able to get a license very shortly after we finish the last test. And at that point, we can start production. It takes about a year to build. and about a year to do the startup tests that need to be done before it can be on the grid. 2 years from the time that you have the order, the site license, and you have the local building permits before we can put power on the grid. It lets you respond quickly to changes in demand. If the plant was cold, like it would be when we first install a power plant, we use diesel, which is about a 1 megawatt electric, to preheat the aux boiler and run pumps. Then we use the aux boiler, which is about 50 megawatts thermal, to heat up the salts and the piping and the turbine generator and generate some steam flow through the turbine. We use the Century turbine to use that steam to generate 15 megawatts electric. That provides house load power so it can start pumping salts and seawater and such around. We can then transition to hot standby or island mode, where we would use normal nuclear heat and come down the primary heat transport path to the Century turbine. All of this would be covered by the nuclear side, and then we'd pick up with the Century turbine. And we can sit in that mode for days, years even. And then when you want to ramp up to power up the grid, we have to be sure that our control system understands that you are bringing up the grid so that we widen the window of what is acceptable behavior. We're speccing right now 60-year design life or 200 starts. I want to push that up to 80-year design life. I think there should be no problem with that. 4-year overhaul for turbines. Typical is 3. We're pushing a little further so it coincides with when we're changing the cans. And then we have automatic voltage control so that if you want us to be the primary frequency control or a secondary voltage control, we can play those roles. I would expect for the demonstration plant, our focus will be base load. And once that is well in hand, then we'll move on to being able to do more load following. This is a test plant full scale. It uses electricity for heat since we don't have any fission, around 10 megawatts of heat. We can use that to run the pumps at 120% of full speed and verify that we don't get any vibration in the pipes, that everything is snugged down appropriately with the right kind of shock absorbers. We can even emulate accidents. For example, drain the salt and turn the heaters on that are in the drain tanks to mimic the heat that's generated by decay heat and verify the cold wall will extract that decay heat and send it up to the decay heat removal pond. You can see scale with the people there. This is a rather large structure. It's about 30 meters cubed. We can test the salt running at full speed with a small delta T. We can run the salt at a low speed with a large delta T. So we can test a lot of things, but we cannot do full speed and large delta T because that would be too much heat transport. And we can't test any of the neutronics. But it will have thorium and uranium in it. It will be the right density, the right chemistry. We can test the sensors, being able to verify the redox and other such things.
What is the most critical test in the testbed platform? If this test, we're all good to go.
I would think that would be the Fukushima type test. Do a sudden drain, use electric to heat the salt in the drain tanks like decay heat. If you look at the accidents, both 3 Mile Island and Fukushima were accidents that the final trigger was the decay heat. They didn't get rid of the decay heat. The safety system is very confined in a small space and is fully passive. It makes it a lot easier to analyze. You look at the safety system on light water reactor, you have to have a safety system that can overcome very high pressure and force liquid in there. It has to be able to retain high pressure. The safety system on light water reactor is a very impressive piece of engineering. But it takes some impressive analysis for the regulator to even decide when it's safe. In our case, because it is fully passive, it is something that is much more clear that it's safe. When you get a very complicated system, then you got to start thinking, well, what if this and then that? You get a lot of combinatorics that can happen. When you look at any of the accidents, it hasn't been one thing that's failed. It's been when you get a combination of 3 or 4 things that were seemingly independent that things went bad. We need the results from this test when we go before the regulator because they have to sign off that this plant will be safe. They have to be convinced. I think seeing it work is going to be a lot more convincing than seeing our computer printouts. Also, this platform will serve as a test bed for design improvements. So once we've built it, if you have a better idea for what to do with the can, we can install it here and test it out here before we put it in a real reactor. Likewise for lots of other components. So it becomes a long-term test platform for us. All right. Any other questions?
Yeah. No? Okay, very good.
Okay.